Hi students, we are going to review in-class exercises 4 and 5 of electrochemistry in this video. For question 1 of in-class exercise 4, we have strontium metal being abstracted from molten strontium bromide via electrolysis. Do take note of the keyword molten here, because molten here means that strontium bromide is in the liquid phase, it is not in the aqueous phase. Yeah, because if you think about it incorrectly, then you will predict the wrong product at the anodes and the cathodes. So in molten strontium bromide, there are only two ions. One is strontium 2 plus in the liquid phase, the other one is bromide in the liquid phase. Okay, so over at the graphite anodes, I expect bromide to be oxidized. Okay, so it's in the liquid phase. Bromide to be oxidized to give us bromine. At such a high temperature, if you do check up, the melting point of strontium bromide is about 640 plus degrees Celsius. So this whole setup is likely to occur at around 650 to 680 degrees Celsius. So at that temperature, I expect bromine to exist as a gas. So it will be produced as a gas accompanied by 2 electrons. Okay, so plus 2 electrons. And then at the cathodes, I expect strontium to be reduced, okay, by coming in contact with the cathodes. So it will be reduced to strontium metal, okay, but at such a high temperature, strontium metal is likely to be a liquid as well. So I'm going to put in the state symbols as liquids. Okay, then for part B, the question asks, suggest why an atmosphere of argon is used around the cathodes. So you notice that over at the cathodes here, it is surrounded by an atmosphere of argon. I think we can easily reason this out, because strontium being a group 2 metal, its 2 valence electrons is relatively loosely held, and given the fact that strontium is quite low in the in group 2, which means it's just below calcium, but below strontium will be barium, so they are likely to be quite reactive in the presence of oxygen. Yeah, so if you don't want the metal to react upon its formation, then it is better to keep it under inert conditions. Yeah, so the inert condition we can think of will be argon. Yeah, I mean, argon being an inert gas, it is unlikely to react with the strontium freshly produced. Yeah, so what you can easily write out as an answer would be strontium being a highly reactive metal. It can easily react with oxygen to give us strontium oxide. Okay, so that is one part of the answer you can focus on. You can say that an atmosphere of argons instead of the normal atmosphere we are living in will prevent the oxidation of the newly produced strontium to give us strontium oxide. If you wish to, you can also highlight that strontium is likely to react with the water vapor in the air, and in the process we might end up with strontium hydroxide on the surface. Okay, so these are two possible byproducts or side products if it is produced in atmospheric condition. Okay, then for part C, we were told that a current of 5 ampere was passed through molten strontium bromide for 60 minutes. So we are required to calculate the coulombs pass through. So we can do that quite easily. So if you recall the lectures on electrochem, you will introduce that the charge transfer, which is Q, is equals to the product of the currents multiplied by the time. Okay, we are given the current, so that's 5.0. We are given the time to be 60 minutes, so 1 minute is 60 seconds, so we're going to multiply 60 by 60. Okay, so if we punch the calculator, we'll get about 18,000 coulombs. Okay, so that's for part 1. Okay, so this is part 1. And then for part 2, the mass of strontium metal form. Okay, so we know that the charge transfer is also equals to the number of moles of electron transfer multiplied by Faraday. Okay, so if you check out your data booklets, Faraday is 96,500. Yep, so therefore the number of moles of electron transfer is equals to Q, which we have gotten from part 1, 18,000 Okay, so divide by the Faraday constant, that's 96,500, and then we'll be able to get 0.187 moles. Okay, this is the number of moles of electron transferred. Yeah, so you need to be very clear what you are calculating. So over here we are calculating the number of moles of electron transferred, yeah, which is 0.187 moles. From here, we cannot straight away calculate the mass of strontium metal form, because earlier on we know that the stoichiometric ratio between strontium metal and electrons is 2:1. Yeah, so in order to calculate the number of moles of strontium metal, we need to divide this value by 2. Okay, so therefore from here we can calculate the mass of strontium produced. Okay, so that will be equals to 0.187 divided by 2 multiplied by the relative atomic mass of strontium, that will be 87.6. okay, yeah, then from here we will be able to get 8.17 grams. Okay, so do punch your calculator and double check whether this value is correct. Okay, then we'll move on to part D. We will ask explain why explain why aqueous strontium bromide cannot be used to extract strontium by electrolysis. Yeah, so to answer this, we have to take a peek at the standard reduction potential values. Okay, so if you take a look at the standard reduction potential value, you notice that the reduction potential value of strontium is not found. Yeah, so does that mean that we can't do this question? No, we can use the value of calcium and barium as an approximation. We are given calcium to calcium, that's minus 2.87 volts. We are also given barium to barium, that's negative 2.90 volts. So that means that I would expect the reduction potential of strontium to strontium to be between minus 2.87 to minus 2.9. Okay, so that is a very negative reduction potential. And what are we comparing it with? We are comparing it with the standard reduction potential of water H2. Yeah, so this is the one we are comparing with. So you notice that the standard reduction potential of strontium to strontium is likely to be more negative than that of water H2. Yeah, so because of that, I expect water to be reduced to hydrogen gas, okay, or to be preferentially reduced to hydrogen gas at the cathodes, rather than strontium metal being reduced at the cathodes. Okay, yeah, so that should form the bulk of your answer over here. If you are not sure what to write, I think the first thing you need to highlight is that the standard reduction potential of strontium to strontium is likely, my apologies for the pen, okay, so it's likely to be between negative 2.87 volts to negative 2.90 volts, which is significantly more negative than that of the reduction potential of water H2. Okay, yeah, so because of that, that means that H2O is preferentially reduced at the cathode instead of strontium 2+. Okay, so therefore hydrogen gas will be produced. I mean, if you want to continue writing, you can. Hydrogen gas will be produced instead of strontium. Okay, so I hope that will be that is how you should draft your answer. Do take note, as I mentioned many times, whatever I've written here is just a very rough way, a very skimpy way of drafting the answer. I have showcased some of the thought process. So if you are copying down the answer as it is, I don't think you should do that. These are the main ideas, so you should catch some of the main ideas and then craft out the answer on your own. Okay, for question 2A, right? Over here we have sodium chlorate. Is an important industrial chemical. So many thousands of tons, okay, is being produced or is being used each year in the manufacture of chlorine dioxide bleach for the paper industry. It is made commercially by the electrolysis of brine in a cell with no diaphragm, so that the solution at the anode and cathode mix up. Okay, so the details, I don't think you need to go into that because the nature of the question does not require all these details. But what is really important for you guys would be the two equations over here, because for the first equation, it involved the reduction of chlorides to give us, or rather, sorry, it involved the oxidation of chlorides to give us chlorates. Okay, so it's written out in a relatively weird manner. So usually we'll write the 6 electrons on the right hand side. That's why earlier on I get a little bit confused. Yeah, so I'm sure some of you might get confused as well, and this is not uncommon. So when you are doing question, sometimes you just need to make sure that you read the information accurately and correctly. Yeah, so do not rush through question in exams. Okay, so first of all, we are required to calculate the current needed to produce 1 ton. You are told how much is 1 ton. That's 10 to the power 6 grams of sodium chlorate per day. You were told that 1 day, that's 24 hours. I mean, that's obvious. So therefore, the amounts of sodium chlorate, NaClO3. Okay, remember to include the Na. Some of you did not include the Na. Okay, 1 times 10 to the power 6. Okay, and then I divide this by 23.0 plus 35.5 plus oxygen is 16 times 3. Okay, if I take out the calculator and punch, I should be able to get 9.390 times 10 to the power of 3 moles. Okay, so that's quite a bit. And then if I produce this amount, so that will be equivalent to ClO3 minus, and then the stoichiometric ratio between chlorate and the electron transfer is 1:6. So therefore, number of moles of electron transferred, okay, will be equals to 9.390 times 10 to the power 3 multiplied by 6, and then I take out the calculator and punch the values. 5.634 times 10 to the power 4 moles. Okay, so since we know that Q is equals to the number of moles of electron transferred multiplied by Faraday, then we will, and this is also equals to currents multiplied by the time, we can therefore calculate the currents by equating the number of moles of electron transferred, that is 5.634 times 10 to the power 4 multiplied by the Faraday constant, that's 96,500, divide by the time. So the time is 24 hours. So in 24 hours, 1 hour we have 60 minutes, 1 minute we have 60 seconds. Okay, and then once I punch the calculator, I will get a very weird value. It's a super huge value. I'm going to get like 6.29 times 10 to the power 4 ampere. That's a huge number. Okay, but for the industry that might be viable, I'm not sure. Okay, yeah, so that's the number you're going to get. If you're doubting your answer, you can double check and see whether you have gone wrong anywhere. Okay, and then for part 2, calculate the volume of hydrogens measured at RTP that is also produced. Okay, so over here in the process, 3 equivalent of hydrogen gas is being produced. Okay, so that means that the ratio will be 1 equivalent of ClO3 minus to 3 equivalents of hydrogen gas. Yeah, so one way you can do it is simply just multiply this value by 3, or you can simply just divide this value by 2. It's up to you how you want to do it. Okay, you can just straight away calculate. So volume of hydrogen produced is equals to I choose to do it this way, 9.390 times 10 to the power of 3 multiplied by 3. Okay, and then multiply by 24, since I'm told that I'm supposed to calculate the volume at room temperature. Okay, so that will give me 6.76 times 10 to the power of 5 dm cube. Okay, yep. Right, so we are done with in-class exercise 4. So now we'll move on to in-class exercise 5. Okay, so for question 1, we are to use the data booklet to calculate the E cell of a cell composed of the standard copper 2 copper and the standard nickel 2 nickel. Okay, so I'm just going to show you where to find the information. So nickel 2 nickel is negative 0.25 volts, and then copper 2 copper is positive 0.34 volts. Okay, so the reduction potential of copper 2 copper is more positive than that of nickel 2 nickel. So I would expect the copper electrode to be the cathodes and the nickel electrode to be the anodes. Okay, so with that, I think we can easily calculate the E cell. So the E cell will be E reduction. Okay, so that will be copper 2 copper minus E oxidation. So that will be nickel 2 nickel. Okay, so with that, I'm going to get 0.34 minus 0.25. Then I'll end up with 0.59 volts plus 0.59 volts. Okay, so that will be the standard cell potential. Then for A2, predicts how the voltage of this cell would change, if at all, if the nickel 2 half cell or the concentration of nickel 2 was reduced. And then you're supposed to explain your answer. Yeah, so of course, I'm going to base my answer on this particular equation which I've written above. Okay, in A2, I was only told that the concentration of nickel 2 will be reduced, but I'm not told about the copper 2 copper half cell. Okay, so that means that over here, I'm able to say that this value will remain constant. Okay, I think such a conclusion shouldn't be too tall an order. So this will be a constant value. Okay, so I'm talking about A2 now. Okay, then nickel 2 concentration is reduced. So first of all, we need to write an equilibrium expression involving nickel 2 to give us nickel. Okay, so that's nickel solid. Yep, so over here we are aware that when the concentration of nickel 2 is being reduced, I expect the position of equilibrium of the reduction of nickel 2 to become more negative. Okay, so this because this value is given to us as negative 0.25 volts. Yeah, so if the reduction potential of nickel 2 nickel is more negative than 0.025 volts, I expect the E cell to become more positive, because a constant number minus a more negative number, I will end up with a more positive value. Okay, so again, I'm verbalizing some of the thought process which should be included in your answer. So I'm not gonna write everything out. Yeah, so therefore I expect this POE to shift left, which will result in more negative E cell, sorry, not E cell, more negative nickel to nickel. Okay, then this will result in more positive E cell. Okay, yep, E cell. Right. Okay, then next we are looking at part B, which is quite a standard question you expect from any major assessment. So it's either we test you in blocks or we test you in prelim, or you might even get it for A levels, or maybe you might not get it at all. It really depends on how much we want to emphasize on this learning objective for the electrolytic purification of copper. Okay, so over here we were told that when a particular copper ore was reduced, an alloy was formed which composed mainly of copper. So you have nickel and silver as the main impurities. Usually for any respectable question, they will often give you impurities with one metal being more reactive and the other metal being less reactive. That's because they want to ensure that you know how to discuss the tool. Yeah, so it contains no other metal. In order to purify, the alloy was made the anode of an electrolysis cell. So they are quite kind to the students. So they tell you that your alloy must be made the anodes. So that means you are forcing an oxidation reaction there. So you have a pure copper cathode, this is obvious, and then copper sulfate as the electrolyte. With reference to relevant E0 values, explain what happens to the nickel and silver impurities during the purification process. Yeah. So you should notice that, you should take note that there is definitely a need for me to write out the reduction potential values of the three metals involved. First one is copper to copper, which is 0.34 volts. The other one would be silver plus silver. That will be 0.80 volts. Okay, and then the final one will be nickel to nickel. That will be, sorry, I think it's quite difficult to write for today, negative 0.25 volts. Yeah. Okay, so first of all, right, there is something which you need to be aware of, although sometimes when you were learning it, it wasn't emphasized. An external power supply is being used to force out an oxidation reaction at the anodes, because if you just put the electrode there, it will not oxidize on its own, or it might not oxidize to a great extent. Of course, for copper it won't oxidize, but for nickel maybe after a long time. Okay, so that is something you need to be aware of. Yeah. However, for the external power supply, the industrialist, when you're designing the electrolytic plant, right, you have the liberty to adjust the voltage such that only copper will be oxidized. Yeah, but not silver. Yeah. Why is that the case? Because if you compare the reduction potential of copper to copper and silver to silver, right? So sorry, silver 1, silver, right? You notice that they are quite different. So it is possible for me to use the voltage in order for one metal to oxidize instead of the other. Yeah. However, because nickel is more reactive than copper, right? If copper were to be oxidized, then nickel will be oxidized as well. So it's no choice. Yeah. So therefore, from here, right, you can sort of make a conclusion that because of that, I expect that at the anodes, two reaction takes place. That is the oxidation of copper to copper 2. So copper 2 will enter the solution as the copper 2 ions, and then because because nickel is more reactive than copper, if copper were to be oxidized, then nickel will be oxidized as well. Yeah. However, this is not a major issue because nickel, if you read through the question, right, nickel is actually an impurity, so it's not present in large amounts. Yeah, maybe just less than 0.1%, so it doesn't matter. Yeah, so nickel will also enter the solution as nickel 2. Yeah, then what is going to happen to silver? Silver will end up as the anode sludge. So silver will end up as the anode sludge. The reason being, the reduction potential of silver plus silver, right, okay, is more positive than that of copper to copper. Yeah, so it's important for you to highlight this particular reason when you explain. Okay, so you end up as the anode sludge, and then after that, how should you go on to explain? Okay, then at the cathodes, what happens at the cathodes? Yeah, because at the cathode, right, the cathode will attract all the anion present. Yeah, so at the cathodes, I expect copper 2 to be reduced to copper. Okay, so copper 2 plus to be reduced to copper. So I'm going to get copper solid here. Yeah. However, nickel 2 will not be reduced to nickel, and nickel 2 will remain in the solution. Yeah. The reason being, because nickel, the reduction potential of nickel to nickel is more negative. Okay, so sorry, it's more negative than, sorry, I think there's something wrong with the pen. I can't. Okay, it's more negative than that of copper to copper. Okay, yeah. So because of that, I expect copper 2 to be preferentially reduced at the cathodes. Okay, so therefore copper 2 will be reduced preferentially, okay, at the cathodes. Okay, yeah, so that's how you should be drafting your answer, and then nickel 2 will remain in the solution. Okay, yeah, so you can say nickel 2 will remain in the solution. Okay, and that's how you can end your discussion. Okay, then for part C, currents of 2.00 ampere was passed through the cell described in B for 23.0 minutes, and the electrodes removed, washed, dried, and weighed. And then it was found that the anode had lost 0.950 gram. Okay, then after filtering it off and drying it, the deposit below the anode was it weighed 0.05 grams. Okay, so this is extremely important information, because this tells us that the anode sludge weighed 0.05 grams. So this is the silver. Okay, then on adding an excess of dimethyl glyoxime to the electrolytes, the highly insoluble red complex with the formula blah 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 nickel something something was precipitated. Its mass was 0.492 grams. C part 1 is an interesting part. They ask you to calculate the expected increase in mass. Yeah, so expected increase. Okay, so how can we calculate the expected increase in mass when we know that the mass loss due to the anode, right, or the mass loss of the anode is due to a combination of silver falling off as the anode sludge, some of the nickel might get oxidized, and of course the bulk of it is copper. Never mind about that, because we were told the currents and we were told the time, so the charge transfer should be constant. Okay, so that's due to the conservation of charge, of course. So that's Q is equals to IT, which is equals to the currents, 2.00 multiplied by the time 23 minutes multiplied by 60. Okay, so I'm going to get 2760 coulombs. Okay, yeah, then the number of moles of electron transferred, that will be in the reduction of copper 2 to copper. So number of moles of electron transferred is actually equals to 2760 multiplied by 96500. 96500. I'm sure you know how this came from, because the charge is also equals to the number of moles of electron transferred multiplied by Faraday. Okay, then we can calculate the number of moles of electrons. That will be 0.0286 moles. Okay, so I can easily calculate the number of moles of copper. So that will be 0.0286 divided by 2. So that will be 0.0143 moles. Okay, and then of course the mass of copper deposited is also the expected increase in mass. So mass of Cu deposited, okay, equals to the expected increase in mass. Okay, so that will be equals to 0.0143 multiplied by the relative atomic mass, that's 63.5. Okay, from there I'm going to get 0.908 gram. Okay, yeah, then for part 2, supposed to calculate the actual masses of copper, nickel, and silver removed. Silver is straightforward because we were already told. So the mass of silver removed is 0.05 grams. Okay, so mass of Ag removed is equals to 0.0500 grams. We were told about it earlier on. And then the mass of nickel we can easily calculate because we know the formula of the insoluble red complex. Okay, so we can calculate the number of moles of complex. That will be equals to 0.492 divided by the relative atomic mass, relative molecular mass. Okay, we can just use the calculator and sum it up. We should be able to get 288.7. then we'll end up with 0.00170 moles, or you should write it as 1.70 times 10 to the power minus 3 moles. Okay, then amount of nickel 2 is then okay, so this is also the same as the amount of nickel 2 formed. Okay, so this is similar, this is the same as the amount of nickel 2 formed. Okay, and then from here we can determine the mass. Okay, so the mass of nickel removed is equals to 0.00170, okay, multiplied by the relative atomic mass, that's 58.7, and we'll end up with 0.100 grams. Okay, then the actual mass of copper, so mass of copper removed will then be equals to 0.950 minus 0.100 minus 0.0500, and then I'll end up with 0.800 grams. Okay, that's about it. I hope you find electrochem calculation relatively straightforward, not as difficult as acid-base equilibrium, I hoped. Okay, next we'll move on to question 2, where we are working on anodization. Okay, so we have aluminium, so third most abundant element in the Earth's crust. Object made from aluminium may undergo a process known as anodizing. So we are supposed to draw a diagram of an electrolytic cell that can be used to anodize an aluminium object. Label clearly the materials used as the cathode and anode and indicate the electrolyte used. Okay, so I'm sure you have this in your lecture notes, but nonetheless I'm just going to draw one out for you. Okay, so we should have two electrodes. Okay, one on the left, one on the right. Okay, there isn't really a need for you to memorize anything here, but just to ensure that you know what exactly is going on. Okay, so the longer one, remember, for the battery, the longer one is always the positive terminal. Okay, so therefore on the left we have the anodes. Okay, so this will be the aluminium anodes. Then the one on the right hand side will be the cathodes, so that will be the platinum cathodes. Okay, and then we have the solution level. Okay, then I think it's better to just indicate it, so I'm going to put the anode as plus and the cathode as minus, and then the solution is dilute sulfuric acid H2SO4. Okay, so that's about it, and then states the half equations, half reactions that occur at each electrode. So at the cathode, I'm going to have the reduction of hydrogen ions, okay, to give us hydrogen gas. Okay, and at the anodes, I'm going to expect the oxidation of aluminium, okay, in the presence of water, okay, to give us Al2O3 solids plus 6H plus plus 6 electrons, okay, and of course 3 H2O over here. Okay, yep, so largely recall, so I think that should be okay. Then for part C, give one example of an anodized aluminium object. I think you can, there's a lot of examples which you can use. For example, window frames, drink cans, and then you also know that anodizing increases the thickness of the corrosion resistance Al2O3. Okay, so remember that Al2O3 is corrosion resistance. Yeah, I think this is very important. Yeah, so one way to make material more durable is to ensure that the corrosion layers is thickened. Okay, and then in that case the material will be more long lasting. Yeah, then another way you can also include as part of your example will also be the Al2O3 layer is porous, and therefore it allows dye molecules to intercalate between the layers, and therefore your object will look nicer. Yeah, so that allows your aluminium, let's say if you are using it as a casing, right? Yeah, it will be more visually appealing. Okay, so with that, we have come to the end of the review to in class exercise 4 and 5, and I hope you have enjoyed the review video.